Hello students, in this session we have to study the Lamport Shostak Pease algorithm. So before studying this algorithm, we have to understand some basic things. What is agreement, what is consensus in distributed system or blockchain. Blockchain is a distributed system. So we will start with the basic things and then we will try to understand this algorithm. Lamport Shostak Pease algorithm. Before studying this algorithm, we have to understand what is agreement, or we can say what is consensus. Nodes in blockchain often compete as well as cooperate to achieve common goals. So, what is the aim of consensus algorithm? To agree on some common value, to agree on some common goal. All the nodes will compete to each other, and the ultimate goal is to achieve some common goal. In this consensus or agreement mechanism, mutual trust or agreement is very much required between the participating nodes. When there is no failure, reaching an agreement is very easy. When there is no faulty node, malicious node, when there is no failure, then reaching an agreement between the participating nodes is very easy. And this agreement or consensus protocols helps to reach an agreement in presence of failures. But in real time scenario, there may be failures, nodes may fail, some nodes may misbehave, there may be a Byzantine faults. Byzantine faults are very hard to detect. Some nodes are failed, some nodes are misbehaving, but it is very hard to detect that misbehaving nodes in case of Byzantine faults. In case of such type of faults, it is very difficult to achieve the consensus among the participating nodes. In previous sessions, we have studied the Paxos and RFT algorithm. In this, we have to study Lamport Pease, Lamport Shostak Pease algorithm. What is the system model for agreement, or you can say consensus algorithm? Agreement protocols have been studied under following system models. Uh, this agreement protocols are studied under some scenario, and that scenario consists of n processors, and out of this n processor, m processors can be faulty processors. Processors or nodes can directly communicate by message passing. Participating nodes can communicate directly through the message passing, and receiver knows the identity of the sender, and communication medium is reliable, and only processors are prone to failures. Processors may or nodes may fail. So this is the system model where there are n processors, and out of n processors, m processors may be faulty, communication medium is reliable, and only processors may fail. There are two types of communication: synchronous communication and asynchronous communication. In synchronous computation, not communication, there are two types of computations: synchronous and asynchronous computation. In synchronous computation, processor run in lockstep manner. That means processor receives the message, it performs some computation, and after performing the computation on that message, it sends a message to other process, or it may send the reply message. This happens in synchronous manner. The processors are synchronized on common clock. But in case of asynchronous computation, computation does not proceed in lockstep manner, and processor can send or receive messages and performs computation at any time. Internet is the best example of asynchronous communication. In that communication, we receive the messages at any time, and we check that messages whenever we get the time. So there are two types of computations, synchronous and asynchronous computations. So there are different models of processor failures. Processors or nodes can fail in three modes. The first type of fault is called crash fault. Processor stops. Processor stops working and it never resumes the operation. That processor permanently gets detached from the distributed system, or we can say blockchain. Then second type of fault is omission fault. Processor omits to send the messages to some other processors. Processor will receive the message, but processor will not forward that messages to other processors. It will simply ignore that messages. So this type of fault is called omission fault. Then third type of fault is malicious fault. This fault is also known as Byzantine fault. Byzantine faults. In that malicious fault, processor send false messages to confuse the others. So this type of fault is very difficult to handle. Processor can change the messages, processor can force the messages, and processors can confuse to other processors. Such type of faults are said to be Byzantine fault. Processors are misbehaving, but we don't come to know that processor is misbehaving. Processors are failed, but we don't come to know in blockchain or in distributed system that processor has been failed. So such type of misbehavior or is called Byzantine faults, and it is very hard to detect, and also it is very hard to correct such kind of faults. So there are two types of messages: authenticated messages and non-authenticated messages. The meaning of authenticated messages is that the authenticated message is a signed message. It may be signed by digital signatures, or some other cryptographic method can be used to sign the messages, and processors cannot change or forge this type of authenticated messages. This processor can verify the authenticity of the message, and it is in case of say this authenticated messages, it is very easy to reach an agreement between the participating nodes in the blockchain or distributed system. But in case of non-authenticated messages, such type of messages are not signed, and such type of messages are also known as oral messages. Processors can change or forge the message and claims to have received the message from others. So we cannot verify the authenticity of non-authenticated messages. So in such kind of non-authenticated messages, it is very difficult to reach an agreement between the participating nodes. Then classification of agreement problems. Agreement problems, or we can say consensus algorithms. So first type of agreement problem is called Byzantine agreement problem. In that Byzantine agreement problem, a single value is to be agreed upon. All the nodes will agree on single value, and agreed value is initially proposed by the arbitrary node, or we can say primary node or source node. Agreed value is proposed by source node, and all non-faulty processors agree on that value, on that initial value. Whatever the value is proposed by the source node, all the nodes will agree on that value. Such type of agreement problem is called Byzantine problem. Then second type of agreement problem is consensus problem. That is very relevant to the blockchain. So in blockchain, every processor has its own value. In consensus problem, every processor has its own value, and all faulty processors agree on common value. Every processor has in one value, and all the processors has to agree on some common value. And such type of problems are said to be consensus problem. That we are studying this problem from the unit 1. So this blockchain is based on the consensus mechanism. Uh, in this consensus problem, every node has its own value, and all the nodes has to agree on that some value. Then what is consensus problem that we are studying from? Already we are studied about this problem, and we have discussed many times about this consensus algorithms. Every processor will broadcast its initial value to all the processors, and initial value may be different for different processor. Different processor may have their different values, and protocol, this consensus protocol must meet following requirements. The first requirement is agreement. All non-faulty nodes agree on some single value, though the nodes have their different values, but all these nodes have to agree on the some common value, or you can say single value. Then second type of uh, requirement of this consensus problem is validity. If the initial value of all faulty processor is V, then agreed value must be V. This is the second requirement of this consensus problem. Then what is the solution for Byzantine problem? In that Byzantine problem, every node has to agree on that single value proposed by the source node, or you can say primary node or arbitrary node. This solution is first defined and solved by the Lamport. So in this Byzantine agreement problem, the solution is that the source will broadcast, source, or we can say primary node will broadcast initial value to all other nodes, and processors send their value to other nodes and also relay the messages. So in this solution, there is a primary node or source node that will broadcast value to all other nodes, and processor will send their own values to other nodes, and processor send their values to other nodes, and also relay whatever the messages processors will receive, that messages also the processors will forward to other nodes. So in this scenario, the faulty processors may confuse by sending the conflicting values. So what to do with such kind of faulty processors that may confuse to the whole system and all the processors participating in the network? So if faulty processors dominate in number, if faulty processors are more than the non-faulty processors, then these faulty processors can prevent non-faulty processors from reaching an agreement, because the faulty processors are more in number and they will dominate the non-faulty processors, and they can prevent non-faulty nodes from reaching an agreement. The requirement of this Byzantine agreement problem, requirement of this solution provided by the Lamport is that number of faulty nodes should not exceed certain limit. So we have studied in the Paxos also. Paxos puts the limitation on the number of faulty nodes. So the number of faulty nodes must be less than 50%, that we have studied in the Paxos. If that number of faulty nodes are more than 50%, then these nodes will dominate the non-faulty nodes, and these nodes can prevent from reaching an agreement. So this is the requirement of this Lamport, that the number of faulty nodes should not exceed certain limit. So this is the solution proposed by the Lamport for Byzantine faults. So what is the now main objective of this session is to study this Lamport Shostak Pease algorithm. So this algorithm is based on the value that all the nodes has to agree on that value, and if the majority of the nodes agree on that value, then that value is finalized. So this is the basic concept of this Lamport Shostak algorithm. So this is based on a majority value. If the majority of the nodes agree on some value, then that will be the agreed value, or you can say final value. This algorithm is known as oral message algorithm, OM in bracket M. OM algorithm, where M is the number of faulty processors and n is the number of non-faulty processors. So there are n number of non-faulty processors and m number of faulty processors. So this algorithm works as follows, and it is based on the majority voting. If the majority of the people, if the majority of the processors nodes agree on that value, then this algorithm will finalize that value. It will that will be the agreed value, or we can say finalized value. This algorithm works as follows. Source processor sends its value to every node. Source, or we can say primary processor. That in Paxos also we have studied the primary or proposer. Proposer node will send its value to every processor, and each processor uses the value received from the source. So this is the concept. So in this Lamport Shostak Pease algorithm, there is a proposer node, proposer, or we can say primary node, or we can say source node, that proposes a initial value, and every node uses that value received from the source. So you can see the steps of this algorithm. This is based on the majority value algorithm. The value agreed upon by the majority of the nodes. So that value the processor uses in this OMM algorithm. M is the number of faulty nodes and n is the number of non-faulty nodes. So you can see the steps of this OM algorithm. Oral message algorithm. This OM is also called oral message algorithm, or Lamport Shostak algorithm is also called oral message algorithm. This is the alternate name, oral message algorithm, for Lamport Shostak and Pease algorithm. So you can see the working of this algorithm. This algorithm has some steps. You have to remember these steps. If you don't understand this algorithm, then you try to remember the steps of this algorithm. That is enough for studying this algorithm. So you can see the steps. Source will send its value to every processor. Then for each processor I, Vi be the value processor receives from the Vi is the value processor will receive from the source. Then third step is processor I acts as the new source. Processor I will act as the new source, and it will initiate the algorithm OM, and where it sends a value Vi to each of the n-2 processors. So whatever the value the processor will receive from the source, processor will processor will forward that value to the n-2 processors. So for each I and j, you can see the fourth step. For each I and j, Vj be the value processor I received from the j in step 3. Last step is that processor I uses the value majority value v1, v2, so whatever the value it will receive from the majority of the nodes, that value will be used by the processor. So this is the algorithm based on the concept of majority value. So this is about this Lamport Pease and Lamport Shostak Pease algorithm. So in this session, students, we have studied Lamport Shostak Pease algorithm. So we will stop here. Here is the end of this unit also, unit 3rd. Whenever I get the time, I will take one more session of the one more session on BFT, Byzantine fault tolerant. That already we have studied in the Paxos or Byzantine fault. We know that Byzantine fault where the nodes may misbehave, but we don't come to know. It is very hard to detect that the nodes are misbehaving. Some nodes may fail, but it is very difficult to detect that the node has failed. The nodes may change the messages. Nodes may alter the messages, but it is very difficult to identify that node has changed the meshes. So such type of faults are said to be Byzantine fault. This name Byzantine name is derived from the Byzantine general's problem. In that Byzantine general's problem, there is one city, and at the center of the city there is army of the city, and there are two generals, generals A and B. That generals A and B has to attack on the army of the city, and the army of the city is so strong that it was very difficult for one army either A or B to defeat that army of the city. So if these two armies A and B both combinedly attack on the army of the city, then it was possible to defeat that army. So there must be a proper communication between A and B. If A and B at the same time attack on the army of the city, then it may be possible to defeat that army. So there must be a communication, and if that communication is not proper, if someone is attacking, if A is attacking and if B is not attacking, then this army of the that city may defeat A, and so this problem is derived from such kind of scenario. So such type of where A may the node A may misbehave, it may send wrong message to the army general. So such type of faults where the nodes may misbehave, nodes may fail, and it is hard to detect that the node has been failed, because these armies are at different locations, to the opposite sides of the city, and if they attack at the same time, then it was possible to defeat the army of that city. But A may misbehave, B may misbehave, A may send wrong message, army A may fail or B may fail. Such kind of scenario may happen, and this Byzantine fault term is derived from such kind of scenario. So this is all about this session, and also this is the end of this unit, and if possible I will take one more session on the for explanation about the Byzantine faults. So today we will stop here. Thanks for watching session. Goodbye.